Okay, we're continuing with Chapter 8 in the trigonometry textbook. Right now we're learning about complex numbers. In this video, we're going to go through section 8.3, which is on the product and quotient theorems. So what we're talking about here is we already learned how to multiply and divide complex numbers, but we learned how to do this in the rectangular form. In this section, we're going to learn how to do this from the perspective of the polar form or the trigonometric form. Okay, so products of complex numbers in trigonometric form. Using the FOIL method to multiply complex numbers in rectangular form, we find that the product of 1 plus I root 3 and minus 2 root 3 plus 2I is as follows. So, okay, yeah, we know how to, if we wanted to find the product of these two complex numbers, okay, we know how to do this. We're going to get, so just multiply it like normal, minus 2 root 3 plus 2I minus, and then 2 times 3, this is going to be, so minus 6I plus, and then 2 root 3 I squared. So, okay. This is going to be, you have minus 2 root 3 minus 2 root 3, so minus 4 root 3, and then plus 2I minus 6I, that's minus 4I. So there we go. We multiplied two complex numbers in rectangular form and got a new complex number in rectangular form. All right? But now they want us to look at what if we first converted these two complex numbers to polar form and then multiplied them. So, okay, we know how to convert to polar form. This is because we have r is equal to square root of x squared plus y squared, and we know how to do this from the previous section. So they convert these two complex numbers to polar form. Then they multiply these two numbers out. Now, just note, though, again, I really want to make this clear that we're taking complex number 1 and multiplying it by complex number 2 to get complex number 3. Okay? Whether or not we're in polar or rectangular form doesn't change the, like, this is still, look, these are equal, right? This is still complex number 1. This is still complex number 2, right? We've got the rectangular and the polar form. It's the same thing. So when we multiply them, we're going to get Z3. It's just going to be in a different form. It's the same numerical value, the same vector. It's the same exact vector in 3D space. We're not changing anything about the actual, I guess you could say, physical nature of this. Okay, so, like, again, we're in the complex plane, and we're multiplying two complex numbers and getting a third complex number. Let's say it's, when it would be minus, somewhere around here, minus 4 root 3 minus 4I. That's Z3. We're not changing Z. When we change forms, we're still going to get multiplying one number by another number and getting this Z3, no matter what form we're in. It's really important to understand that. Okay, so here's the two complex numbers in polar form. They're going to multiply this out. So, okay, they bring the 2 and the 4 out front here, and then distribute the cosine 60 plus I sine 60 and the cosine 150 plus I sine 150. And so they get a bunch of terms here, and then they simplify, like the I squared becomes minus 1. They simplify and get, so this 8 times, and then so cosine 60 times cosine 150 minus sine 60 times sine 150, plus, and they group the I terms together, I times sine 60 times cosine 150 plus cosine 60 times sine 150. Okay, but you can see that this is representative of the sum and some of the sum and difference identities. This one's for cosine, this one's for sine. So they can write this as 8 times cosine of 60 plus 150 plus I times sine of 60 plus 150. That's what it simplifies to. And so 60 plus 150 is 210. So here's the final answer. That's Z3. If we took the cosine of 210, the sine of 210, and distributed the 8, we get this. Okay? Now, but what's interesting, though, is that it's kind of, if you represent a complex number in polar form and do a multiplication, it's kind of has an intuitive way of looking at it in polar form, the multiplication. So it says the absolute value of the product, 8, is equal to the product of the two absolute values of the original complex numbers. That's nice, right? It's just the product, Z3 in polar form, the radius is just 8. And it's always going to be positive because we know the standard form for polar is it's always a positive r. So you just multiply. If you're multiplying two complex numbers, you just multiply to get the radius of the final result. You just multiply the radiuses of the two complex numbers. Okay. So what about the angle, though? Well, okay, the angle is just the sum of the arguments of the two original complex numbers, right? 60 plus 150. So that's really easy. That's significantly easier than doing the FOIL method with the rectangular form. Now, I mean, it's not like it was that hard multiplying two complex numbers with the FOIL method in rectangular form, but still, I mean, maybe if you're multiplying a bunch of complex numbers, or it would be a lot easier to convert them to polar form, or it's just maybe it's a lot more intuitive just to think about the meaning behind it when you're thinking about it in polar form. Okay, so yeah, they point this out, though, and it's so important to note that when they simplify this, they get the exact same. It's the same number. It's the same vector. So a complex number is a vector, right? It's not a number. But no matter what form you have the complex number vector represented in, you're not changing the vector when you change forms. You're just changing how you represent the same vector. It's the same exact vector with its tail at the origin. All right, so the product theorem, if you have two complex numbers in polar form, then and you want to multiply them, the result is R1 times R2, the cis theta 1 plus theta 2. That is to multiply complex numbers in trigonometric form, multiply their absolute values, and add their arguments. Cool. Okay, and just to show you how easy this is, let's multiply these two complex numbers. Well, 3 times 2 is 6. 45 plus 135 is 180. Done. That's it. Now we can simplify this. So cosine 180 is going to be minus 1. Sine of 180 is going to be 0, so minus 6. Okay, now what about quotients of complex numbers in trigonometric form? Remember, in rectangular form, we had to use the complex conjugate to evaluate this. Wasn't too bad. So, yeah, let's do that. So if we wanted to find what is this complex number, Z1, divided by this complex number, Z2, well, we multiply by 1 in the form of the complex conjugate of the denominator. Remember, the complex conjugate, you just change what's in the middle here from plus to minus in this case. You don't worry about this sign out front here. So minus 2 root 3 minus 2i. So let's see. In the numerator, we're going to get minus 2 root 3 minus 2i minus 2i root 3 minus 2i squared root 3. And then in the denominator, we're going to get, let's see, so minus 2 root 3 times minus 2 root 3 is 4 times 3 is 12. Okay. And then, let's see, minus 4i squared. Okay, minus 2 root 3 minus 2 root 3 plus 2 root 3 is going to be 0. And then minus 2 root 3 minus 2 root 3, so we're going to have minus 4 root 3 I over, and then this is 12 plus 4 is 16. So let's see, that's going to be minus root 3 over 4I. Let's see, did I mess something up here? Minus 2 root 3 minus 2I minus 2I. Oh, this is going to be, okay, minus 6. Because you've got root 3 times root 3 is 3 times minus 2, so, and then, let's see, minus 2I squared root 3. So we've got, let's see, these are still going to subtract out. Minus 2I minus 6I is minus 8I over 12 plus 4. So minus 1/2 I, like that. Okay, but now what if we wanted to divide these two complex numbers in polar form? So let's see. All they do, they don't go through a whole derivation. They just write them in complex form, the two numbers. Then they write the solution in polar form. We know this, the solution in rectangular form is going to be the same as the one in polar form, same numeric, or like as a vector. So they write it in polar form, and they just compare. And they see that it's like parallel to the product theorem in that you're going to be dividing the two radiuses. So 2 divided by 4 is 1/2. And then you're going to be subtracting the angles. So it's going to be, you'll have so R1 cis theta 1 over R2 cis theta 2 is going to be R1 divided by R2 cis theta 1 minus theta 2. Whereas for the product theorem, it was R1 cis theta 1 times R2 cis theta 2 was equal to R1 R2 cis theta 1 plus theta 2. And so that's the quotient theorem. You see, dividing two complex numbers in polar form, you get this here. So it's really simple for multiplying and dividing complex numbers in polar form. So, right, like here, what is this complex number divided by this complex number? That's going to be 2 cis minus 60 minus 150 minus 210. Done. Really cool, right? That's, I mean, extremely quick. If we come over here, let's see. 9.3 cis 125.2. You just, okay, what's 9.3 times 2.7? That's the radius. And then add these two angles and you're done. Same idea here. That's just in the angles are in radians. Okay, so let's work some example problems.